Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through everything you need to know for the upcoming test. So I'll go through each of these subjects listed on the slides. Let's start with parabolas. So a parabola is a graph of an equation of the form y equals ax squared plus bx plus c. So what the parabola looks like depends on these four features. So every parabola will either look like this, a smiley face or a frowny face. And that's determined by a, which is the number in front of x squared, the coefficient of x squared. If a is positive, if this number in front of x squared is positive, then it's a smiley face. And if this number in front of x squared is negative, it's a frowny face. Every parabola has a y-intercept. So if the equation's written in this form, this c value is the y-intercept. That's where the parabola hits the y-axis. So for x-intercepts of a parabola, what we do is we let y equal 0, so we change this to 0, and solve the resulting quadratic. So remember, the two methods we've learned for solving quadratics are factorization and quadratic formula. But just be aware that a parabola may have 0 x-intercepts, so if it looks like this, doesn't hit the x-axis. It can have 1 x-intercept, if the x-intercept is also the turning point, and it can be like this where it has 2 x-intercepts. All parabolas have 0, 1, or 2 x-intercepts, and that corresponds to the number of solutions to the quadratic. So remember we learnt the discriminant. So the discriminant is b squared minus 4ac. That's the bit under the square root sign in the quadratic formula. So if the discriminant is less than 0, then there are no solutions, 0 solutions to the equation, the quadratic equation. That means there will be no x-intercept. So if the discriminant is equal to 0, there will be 1 x-intercept, and if the discriminant is greater than 0, there will be 2 x-intercepts. So let's look at number 4, turning point and axis of symmetry. This is two different features that every parabola has, but we can calculate them at the same time. We use this formula, x equals minus b over 2a. So b is the coefficient of x, and once again, a is the coefficient in front of x squared. So this here gives you the equation of the line of axis of symmetry. The axis of symmetry is always a vertical line, but this formula also tells us the x-coordinate of the turning point. So if we want to find the turning point, then we know the x value, we have to substitute into the original equation to find y value. A point needs an x value and also a y value. So every single parabola has a turning point. If the parabola is a frowny face, then it's a maximum turning point. And if the parabola is a smiley face, then it has a minimum turning point. So if the parabola is a frowny face, it has a highest y value, and it has a lowest y value if it's a smiley face. So this might not make heaps of sense, so let's put this all together in graphing this parabola here. So I want to turn this equation into a graph. Because of this x squared term, I know it's going to be a parabola. So the first thing I need to do is identify a, b, and c. So b is clearly 6 and c is clearly 8. But if there's no number written in front of the x squared term, then it's 1. A in this case is equal to 1. So because a is 1, and 1 is obviously a positive number, this parabola will have a smiley face orientation. It will be like that. So because c is 8, its y-intercept will be 8. So now to find the x-intercepts, I'm going to take my equation and make y equal to 0. So to find the x-intercepts, I need to solve this equation. I could use the quadratic formula, but factorization's probably easiest. Because this is a trinomial with 3 terms, hopefully you remember the way I factorize it. I find 2 numbers that multiply to this and add to this. So those 2 numbers are positive 4 and positive 2. So positive 4 and positive 2 are not the x-intercepts. They're the numbers that go in the brackets when I factorize. So x plus 4 times x plus 2 is this expression factorized. Now we use the null factor law. Either the first bracket equals 0, which means x is minus 4, or the second bracket equals 0, which means x is minus 2. So this parabola will have two x-intercepts, one at minus 4 and one at minus 2. So we've done the first three things. Now we look at the fourth, which is the turning point or the axis of symmetry. So for that, we have x equals minus b over 2 times a, which gives us minus 3. So the axis of symmetry is x equals minus 3. The x-coordinate of the turning point is minus 3. So a trick to let you know if you're on the right track, if you have two x-intercepts, then the axis of symmetry is halfway between them. The turning point is halfway between the two x-intercepts. If you have only one x-intercept, the turning point is that x-intercept. So we found the x-coordinate of the turning point. Now we need to find the y-coordinate of the turning point. So if I'm substituting x equals minus 3 into this equation, I need brackets. Substitute a negative, you always put brackets. So y is equal to x squared plus 6 times x plus 8. Put that all in your calculator and you get minus 1. So that means that the turning point is minus 3 minus 1. So now that we have calculated all of these features, we're just going to plot them and join them up. So we'll start with the y-intercept equal to 8. So I'm just going to plot that there. So now I'm going to plot x-intercepts at minus 4 and minus 2. And the turning point is here minus 3 minus 1. So that will be down here. And remember, of course, because the axis of symmetry is x equals minus 3, this will be the line of symmetry. The parabola will be symmetrical about that line. So now I've plotted all these, I just join them up, knowing the shape of a parabola is either this or this. So the parabola is going to start up here, come down through the x-intercept, it hits the turning point, stops, turns around, and then goes the other direction up through the y-intercept. That is the graph. So my graph needs arrows on the end of it, and I label it with its equation, and then I'm done. All right, let's move on now to graphing circles. So we're looking now at graphing circles as opposed to finding the area of circles, which we'll do a little later in the video. So if the equation is of the form x plus a squared plus y plus b squared equals r squared, that graph will be a circle. Its center is minus a minus b, radius is r. So you have to take the negative of this number to get the x-coordinate of the center, the negative of this number to get the y-coordinate, and you have to square root this to get the radius. So this is different from a parabola because the y is also being squared here. Whereas in the previous slide when we were doing parabolas, it was y equals something times x squared, only the x was being squared. So let's graph x squared plus y squared equals 9. So this last number here is r squared, so that means r, the radius, is just going to be the square root of 9, which is 3. So the radius of this circle here will be 3. Now, because there's no a and b value here, there's nothing in the brackets with the x or the y, the center's actually 0, 0, which is the origin. So this graph has a center here, and it has a radius of 3. So what I do is I start at the center, and I go 3 in all directions. So I'm going to go 3 to the right, 3 up, 3 down, and 3 to the left. And the circle will go through all of those points. So I know that this isn't the best circle ever drawn, but that's what the graph of x squared plus y squared equals 9 looks like. So I also have to make sure I label the graph with the equation. So let's try the one in blue. X minus 1 squared plus y plus 2 squared equals 4, which looks a bit more like that. So we're going to start by finding the center. So the center I'll call C. It's the negative of this. So this is a negative. The center becomes a positive. So the x-coordinate is positive 1, and the y-coordinate is the opposite of this. It's negative 2. This will have a center of 1 minus 2. So its center is going to be down here. Now, because r squared is 4, that number's 4, the radius is just the square root of 4, which is 2. So this is the graph of a circle with center 1 minus 2 and radius 2. So we mark the center, and this time, because the radius is 2, we're going to go 2 in all directions. So we're going to go 2 to the right, 2 to the left, 2 up, and 2 down like that. And so it'll look like this circle in blue. Once again, I apologize, I know it's not the best circle, but that is the graph of x minus 1 squared plus y plus 2 squared equals 4. So that's all well and good for graphing circles when you're given the equation, but let's look at the opposite. When you're given the graph and you need to find the equation. So here we have a circle with center 3, 2. So to find its equation, we know it's going to be x minus that x coordinate, x minus 3 squared, plus y minus 2 squared equals r squared. So now all we have to do is find the radius of this circle. So there are a few ways that you can find the radius. If you know a point on the edge of the circle, you can use Pythagoras, the distance formula. So to go from 3 over here, the x-coordinate 6, so I've gone across 3 and up 4. Because the y value here is 6, so I've gone up from 2 to 6. So using Pythagoras, I have the square root of 3 squared plus 4 squared equals 5. The radius is 5. Of course, in this one, we also know the radius is 5 if it goes up to here at 7. So in this case, I've just given you 2 ways to figure out the radius of this circle is 5. So if r equals 5, it's not x minus 3 squared plus y minus 2 squared equals 5. It has to equal 5 squared. So I'm going to rub out r and replace it with 5. And of course, 5 squared is just 25. This circle is the graph of x minus 3 squared plus y minus 2 squared equals 25. If I were to start with this equation here and turn it into a graph, it would look like that. All right, that's all for the graphing nonlinear relations. Let's now go on to measurement. So in measurement, we're looking at area, surface area, and volume. A lot of it comes down to formula. So make sure you look over the formula for area, surface area, and volume. You will be given a sheet in the test with the formula, but you won't be told which one it is. So I'm not going to go through every single shape for area. That would take too long. I'm just going to go through the 2 that caused us the most problems. So the first is a sector. The second is a trapezium. So this is a sector. A sector is part of a circle. So this is like a slice cut out from a circle. So let's find the area of a circle. Well, we should know now the area of a circle, a full circle, is just pi times radius squared. Of course, this isn't a full circle. So we have to figure out what fraction of a circle is this. Is this a quarter circle? Is it 5/7 of a circle? That's what we have to figure out. So the way that we figure out which fraction of a circle it is, whether it's a half, a third, or whatever, is this angle here divided by 360. A full circle has 360 degrees. This has only 135 degrees. So what we can do is we can take that angle, which I'll call theta, divide by 360. This formula, theta over 360, tells me what fraction of the circle I have, and then I just times it by pi r squared. So for this sector here, the angle theta is 135, so this is 135 over 360 of a circle. In fact, 135 over 360 is equal to 3/8. This is 3/8 of a circle. So we find the area of the whole circle, which is pi times 12 squared. This is the area of the full circle, and we times it by 3/8 because this is 3/8 of a circle. So if we put that on our calculator, we get about 169.65. Now, whenever you're in area, it's units squared. So this will be meters squared, and then we're done. All right, let's look at the shape on the bottom now. This shape here is a trapezium. It's a 4-sided shape with 1 pair of parallel sides. So you just have to recognize that the formula for the area of a trapezium is h over 2 times a plus b. So, for a trapezium, A and B are the two parallel sides. H, when you see H in any formula in measurement, be it length, area, surface area, or volume, H always means perpendicular height. So this side here, the perpendicular height would be H. So the problem here is I want to find the area of this shape, which is hard enough, but I don't actually know H. See, sometimes in measurement calculations, you will need to find an unknown side in order to calculate its area, surface area, whatever. So if there is an unknown side that you need to find in order to calculate area, I want you to straight away think of Pythagoras. Pythagoras is a great tool to help us calculate unknown sides. So you might be thinking to yourself, well, wait a minute, isn't Pythagoras triangles? Well, what we can do is form a triangle. So we have a right-angled triangle here. This distance here is going to be the same as this distance there. They're both equal to H. So I want to find H. I have a right-angled triangle. Now, if it's 23 from here to here and 32 from here to here, then it must be 9 from here to here. This distance must be 9. So now we're going to find H using Pythagoras. So H is a shorter side of the triangle. So we subtract. It's the square root of 15 squared minus 9 squared. You can put that straight on your calculator and you get 12. It's obviously meters. So you minus when you're finding shorter side using Pythagoras, you add when you're finding a longer side. So if H was the longer side, it'd be 15 squared plus 9 squared and then take the square root. But because we're finding a shorter side, it's 15 squared minus 9 squared. You take the square root, you get 12. Now that I know H, I have all I need to find the area. It will be the area of this trapezium, H over 2 times A plus B. So again, A and B are the two parallel sides. So this is just 6 times 55, which gives us 330. And again, area is in units squared. So that's all for area. Let's now move on to some 3D shapes. So we're going to look now at surface area and volume. So we're only looking at surface area and volume of prisms. This shape here, a three-dimensional shape, is an example of a prism. A prism is a 3D shape with a consistent cross-section. This shape here, the triangle, is repeated at the back. So this shape that is repeated is called the cross-section or the base. So when you're finding the surface area of any shape, all you do is find the area of each of its faces and add them up. So for this triangular prism, it actually has 2 triangular faces at the front and the back, and it has 3 rectangular faces. So it's got a rectangular face here, at the other side, and there on the bottom. So I'm going to tell you that these two sides are equal and we're going to calculate its surface area. We're going to find the area of each of the triangles and each of the rectangles. So we'll start with the triangle. So what we have here, a triangle like this that's isosceles, base is 12, the slant height is 10, but we don't know the perpendicular height. See, the area of a triangle formula is BH over 2, and as I said, H always means perpendicular height. So to find the perpendicular height, I'm going to again need Pythagoras. I'm going to divide this into 2 congruent right-angled triangles. I can do that if the big triangle is isosceles or equilateral. So because this is an isosceles triangle, I divide it into 2 right-angled triangles. This side down here will be 6. So if I call that H, then H will be the shorter side of a right-angled triangle, 10 squared minus 6 squared, which is equal to 8. I have found the perpendicular height of the triangle is 8. So what that means is the area of each of the triangles is base times perpendicular height divided by 2, which gives us 48 meters squared. So the total surface area, which I'm going to call TSA, so there are 2 triangles that are 48 each, so I'm going to go 2 times 48. So then I need to add the 3 rectangles. Well, the bottom rectangle is 12 by 20, so I'm just going to add that. And then I have this rectangle here is 20 by 10, and the rectangle at the back is 10 by 20. I have 2 triangles that are 10 by 20, so I can just go 2 times 10 times 20. And so adding all that up, I get 736, so surface area is in units squared. So the surface area of a shape can be thought of as the minimum amount of wrapping paper I would need to wrap up the shape. So if I wanted to wrap this up in wrapping paper, I'd need 736 meters squared of wrapping paper. Volume, on the other hand, is like the capacity. It's the amount of 3D space in the shape. So to find the volume of any prism is very simple. It's area of the base times the perpendicular height of the prism. So we mustn't get confused. Before we were talking about the perpendicular height of just the triangle, but when we're talking about volume, we're talking about the perpendicular height of the prism. So the perpendicular height of the prism is the dimension that's at 90 degrees to the base. So I said before, this here, this shape that is repeated is called the base or the cross section. So if this thing I'm shading in yellow is the base, then the side that's perpendicular to it is this side here. So the height of the prism is 20. Now, we figured out before that this area shaded in yellow is 48 meters squared. Remember, we used Pythagoras and everything. So if you know the area of the base, you just multiply by the height of the prism. The volume here is just going to be area of the base times the perpendicular height of the prism. And that gives me 960. So surface area is in square units, whereas volume is in cubic units. So this would be meters cubed. So we also looked at capacity. Capacity is the same as volume except for the units used. So capacity is usually those units you see associated with liquid, like milliliters, liters, and all that. So simple conversion, 1 meter cubed is equal to 1,000 liters, or 1 kiloliter. So if the volume of this prism is 960 meters cubed, that means its capacity is 960 times 1,000. It would hold 960,000 liters of water. So you may think that's a lot, but think of it like this. If you had a triangular prism in this shape, I mean, this is larger than most buildings, most houses, so that's why it can hold so many liters of water. All right, now we're going to look at surface area and volume of a cylinder. So a cylinder is, for all intents and purposes, a prism. We're going to treat it just like a prism in our calculations. So let's say we have the cylinder here. This is the formula for the total surface area of a cylinder. So you don't need to know it off by heart, but you do need to recognize on the formula sheet that this is the surface area of a cylinder. So to find the surface area of a cylinder, 2 pi r squared is the bottom and the top circle. Pi r squared is 1 circle, 2 pi r squared is 2 circles. And 2 pi r h is the rectangle that makes up this curved surface here. So if we were to calculate the surface area of this prism here, we would just substitute h, the height of the prism, for 18, and the radius for 4. So this is the diameter of the circle. That means the radius would be half that. It would be 4. So it would just be 2 pi r squared plus 2 pi r h, and we can put that straight on our calculator. So putting that on our calculator, we get about 552.92, and of course surface area is in units squared, centimeters squared. So I, however, made an assumption. This would be the surface area if the cylinder were closed, if it had a top and a bottom. But what if this cylinder didn't have a top? What if there was no top here? Well, that would be very similar. We could figure out the total surface area and then subtract the top. So you have to account for that in surface area. When you're finding the surface area, it's only the sum of all the faces that the shape has. So if I were to find the total surface area of this shape with no top, it would be the same surface area I just got, 552.92, but what I would need to do is subtract the area of the top, which is pi times radius squared. And so putting that on my calculator, I get about 502.65 centimeters squared. So just make sure you're aware that the surface area of a 3D shape is slightly different if it has no top. So let's look at volume. So volume tends to be a lot easier than surface area. We don't have to add up lots of different areas, and we don't have to contend with whether the shape has or doesn't have a top. The volume of this cylinder is the same whether or not I have the top. So as I said, cylinders are basically prisms. The volume of any prism is the area of its base times its height. So the base here, or the cross section, as I've also called it, is the shape that is repeated. So this circle down here is repeated at the top. The base here is a circle. So the area of the base here is pi times radius squared. That's the area of the yellow circle. That's the base. So then I just times that by the height of the prism. So if I put that on my calculator, I get about 904.78. This time it'll be centimeters cubed because volume's cubic units. So what would be the capacity? How many liters of liquid could it hold? Well, again, capacity is the same as volume except for units. So the other conversion I gave you was 1 meter cubed is 1,000 liters, and the other one you need to know is that 1 milliliter equals a centimeter cubed. If you know those two conversions, you'll be fine. 1 meter cubed is 1,000 liters. 1 milliliter is equal to 1 centimeter cubed. A centimeter cubed and a milliliter are literally the same thing. So if the volume of this cylinder is 904.78 centimeters cubed, that means its capacity, it will hold 904.78 milliliters of liquid. And of course, you know, to go from milliliters to liters, you just divide by 1,000. So this is about 0.905 liters. So remember, volume of any prism is area of the base times the height. For a cylinder, it's pi r squared, which is the base, times the height. So make sure you recognize pi r squared h on your formula sheet as the volume of a cylinder. So let's now look quickly at a composite shape. So let's look at this weird looking shape on your screen. We're going to find its surface area and volume. So if you get a shape like this and you can't even name it, you don't know what it is, what we do is we divide it into shapes that we do know. So this here is a trapezium. So we have a trapezoidal prism on the bottom and a semicircle, half a circle on top, so half a cylinder is the 3D shape on top. So if I want to find the total surface area of this shape, what I'm going to do is find the total surface area of the half cylinder and then add it to the total surface area of the trapezoidal prism. So we said before that the surface area of a cylinder is given by the formula 2 pi r squared plus 2 pi RH. So that's the formula for a full cylinder. So for half a cylinder, we're just going to divide it by 2. So now we're going to find the surface area of the trapezoidal prism. So note, we don't include the bottom of the half cylinder or the top of the trapezoidal prism. Total surface area only is the sum of the areas of exposed faces. Faces on the surface, hence why it's called surface area. So for the trapezoidal prism, what we're going to have is 2 trapeziums at the front and the back. So there's one here, there'll be one at the back. There's also 3 rectangles. There's this big rectangle at the bottom, this rectangle at the side, and then there's another same size rectangle on the other side. Again, we don't include the top of the trapezoidal prism because it's not on the surface. So that's all we have to do here. Find the surface area of the half cylinder, the 2 trapeziums, and the 3 rectangles. So let's start with the half cylinder. So the diameter is 8, meaning the radius is 4. So it's 2 pi r squared plus 2 pi radius is 4. Now the perpendicular height of the prism and of the half cylinder is 12 centimeters. So 2 pi rh divided by 2. So if I put that on my calculator, I get about 201.06. So let's now do the 2 trapeziums. So the area of a trapezium is perpendicular height over 2 times the sum of the 2 parallel sides. So that's how we find the area of this front trapezium. So if there are 2 of them, we just times our answer by 2. So putting that on our calculator, we get 230. That is the area of the 2 trapeziums, one at the front and one at the back. So let's look at the 3 rectangles. So the rectangle on the bottom, this bottom here is 15 by 12. And the other 2 rectangles that form part of the trapezoidal prism, this one and the one on the other side, they're both equal to 10.6 times 12. So it's just going to be 2, because there are 2 of them, times 10.6 times 12. So if I add up all of this into the calculator, I get 434.4. So I'm just going to add that on. So if I add up all of these numbers, my final answer is about 865.46. So the total surface area of this shape, 865.46. Again, that's in units squared, so write as centimeters squared. So surface area is just adding up the areas of all the faces on the surface. So I'm going to get rid of this calculation, and we're now going to calculate the volume. So as I previously mentioned, volume is a lot easier, because we don't have to contend with all the different faces. There's no chance we might miss one. All we need to do is find the area of the base and times by the perpendicular height. So in this shape, the area of the base is actually a composite shape. So the base here is this shape here, which will be repeated at the back. This is the base or cross section. So all I need to do is find the area in yellow and times it by the height of the prism, which is 12 centimeters. So to find this area in yellow, we have a trapezium plus half a circle. So the trapezium, as we figured out before, h over 2a plus b, that's the trapezium, plus half a circle will be pi times radius squared, and of course we divide by 2 because half a circle. This thing here in brackets is the area of the base. I just get my answer and times by 12. So I already figured out that the area of the trapezium was 115. And the area of this semicircle, putting that part on my calculator, I get about 25.13. So I just add those two together, trapezium plus circle. That gives me the area of the base. And then I'm just going to times that by 12. So putting this in my calculator, I get about 1,681.59, and of course I'm in volume, so it's centimeters cubed. So that means that this will hold 1,681.59 milliliters, so its capacity in liters is about 1.68 liters. Volume much easier, area of the base times the height. So the last thing we need to do in measurement is sort of the opposite. That's when you're given a volume or area and you're finding a dimension. So let's try this question here. A cylindrical can holds exactly 1 liters of liquid. Its height is 12 centimeters. What would be its radius? So if you're ever given the area, surface area, or volume of a shape, and you're asked to find a dimension, like radius, length, width, whatever, you form the equation, you start with the formula, substitute in everything you know, and rearrange for what you don't know. So in this question, we're being told the shape is a cylinder. We're given information about its capacity or its volume. So we need to use the formula for volume of a cylinder. So a cylinder's like a prism, so volume equals area of base times height. Now the base of a cylinder is pi r squared because it's a circle. So this here is the formula for the volume of a cylinder. So let's substitute in what we know. We're told height is 12 centimeters. So volume equals pi r squared h. So h, of course, is just 12. Now, we're told that it holds 1 litre of liquid. So 1 litre is equal to 1,000 millilitres, which is equal to 1,000 centimetres cubed. I want to substitute in centimetres cubed because the height was in centimetres. I need this to be like the same unit, centimetres cubed, if this was centimetres. So what I'm going to do now is I'm going to take away my volume, V, and I'm going to substitute it with 1,000. Now I can solve this equation because there's only one pronumeral. There's only one unknown, which is r. So to get r by itself, I undo everything that's been done to r. So I'm going to start by dividing each side by 12. So I get 83.3 recurring equals pi r squared. So when you're solving equations like this, I want to get r by itself. The squared is the last thing I undo. I have to now undo dividing by pi because what I'm doing is undoing things in the opposite order of operations, the opposite to BIDMAS. So r squared is that. I don't really want to put this on my calculator because that will give me a messy decimal answer. I don't want to round here because my final answer will be inaccurate. Instead, I'm just going to take the square root of both sides. So on my calculator, I have the square root of 83.3 recurring over pi, and that will give me what r is. So to put this on your calculator, just do 83 point and write heaps of threes. 83.3333333, divide by pi, and then take the square root. And so if I put that all on my calculator, I get that the radius is approximately 5.15. Because everything was in centimetres, the radius will be in centimetres. All right, we're done with measurement. Let's go on to the final topic of inequalities. So inequalities are just like equations, except instead of an equal sign, you have these inequalities. So that's greater than, or equal to, and that's less than. So make sure you know greater than points to the right, less than points to the left. So how do we solve these inequalities? Well, you do the same process as for linear equations, but there's only one difference, and that's when you multiply or divide each side by a negative. When you do that, you need to reverse the inequality, and I'll show you what that means in a second. But let's start with an easy one here. X plus 1 is greater than 6. So we're saying, what numbers, when you add 1, give you an answer greater than 6. Obviously, there are infinitely many solutions to this. X could equal 7, it could equal 100, or whatever. So to find all these solutions, though, we're just going to use the same process we would for normal linear equations. If you had x plus 1 equals 6, you would just subtract 1 from both sides. So that's exactly what we're going to do here. So then, plus 1 and minus 1 cancel out. I get x is greater than 5. Any number greater than 5 will be a solution to this inequality. It will make this inequality true. 6 will be a solution because 6 plus 1 is greater than 6 is a true statement. X equals 8 is a solution because 8 plus 1 is greater than 6 is a true statement. Anything less than 5 will not be a solution. So for example, x equals 0 is not a solution because 0 plus 1 is not greater than 6. So x is greater than 5. Any number greater than 5 will be a solution. So what we want to do is display this information, all these solutions, on a number line. So you'd be familiar with a number line here. So to graph the inequality, x is greater than 5. So we're going to start at 5 and draw a circle. And we draw a line over all the solutions. So we want all of these numbers here going to the right. All of these numbers are greater than 5. So just a note, when you're graphing on the number line, you use an open circle when it does not include that value. You use an open circle if you're graphing a greater than or a less than, and you shade in the circle, like a closed circle, if you're using greater than or equal to or less than or equal to, which are these two symbols here. So in my equation here, I'm not including 5 because 5 plus 1 is not greater than 6. It equals 6, but it's not greater than 6. 5 is not a solution. This open circle tells me I have everything greater than 5, but not including 5. Let's look at this one here. So let's start by doing this just like we would for a normal linear inequality. So what we would do first is we would subtract 10 from both sides. So then I would get minus 3x is greater than or equal to 1 minus 10. Now, if I want to get x by itself, I need to divide each side not by 3, but by negative 3. So here, I'm actually dividing both sides by a negative. That's what I meant up here. You reverse the inequality when multiplying and dividing each side by a negative. So minus 3x divided by minus 3 is just x. Minus 9 divided by minus 3 is just 3. Nothing special there. But because I divided each side by a negative, I'm going to reverse the inequality. So it switches to a less than or equal to. So my final solution is x is less than or equal to 3. So we only do that. We only reverse the inequality when we're multiplying or dividing each side by negative. If I multiplied each side by negative 3, I would have reversed the inequality. The reason we do that is when you multiply or divide something by a negative, you change its sign. And when we change the sign, we're changing the sign of the inequality. So what I mean by that, you know that 5 is greater than 3. That's completely obvious. But when we have negative 5 and negative 3, we reverse the inequality. Minus 5 is actually less than minus 3. When we've multiplied or divided each side by a negative, we're changing the sign. We're changing this to a positive, this to a positive. That's why we need to reverse the inequality. So we've got our solution, x is less than or equal to minus 3. Let's graph on a number line. So we'll put 3 in the middle here. We'll put a couple of numbers each side, so 2 and 1, like this. Numbers always go less than to greater than from left to right. The numbers are getting larger. So we're going to start at 3. This time we want all the numbers less than 3. So we draw a line that points to all the numbers less than 3. Now, because this is a less than or equal to, I'm going to shade in the circle. This time I'm including 3 in my solutions. 10 minus 3 times 3 is greater than or equal to 1. This time 3 is a possible solution, hence why it's shaded in. All right, let's do this last one here, which is a little more difficult. So we're just going to treat this like a linear equation. If I have an equation like this, x plus 3 over 8 equals x minus 11, my first step would be to get rid of the fraction. When you have pronumerals on both sides, you either get rid of the fraction or expand the brackets if there are any. And that's what we're doing here. So we're going to get x plus 3 is less than 8 times x minus 11. Now we're going to expand the brackets. So we're not actually doing anything to both sides in this equation, just expanding the brackets. So when we have something like this pronumeral on both sides, we need to get the pronumeral to only one side of the equation. We do that by subtracting the pronumeral with the lowest coefficient. I'm going to subtract x from both sides. So this x has a 1 in front of it, this x has an 8 in front of it, this has a lower number in front, that's why I'm subtracting. So x minus x just gives me 0 on that side, so we're left with 3 is less than 7x minus 88. So what we're going to do now is add 88 to both sides. So we get 91 is less than 7x, and then we're going to divide each side by 7. We get 13 is less than x. that's the same as saying x is greater than 13. If 13 is less than x, then x must be greater than 13. So to graph that on a number line, we'll put 13 in the center, a couple of numbers either side. This time, we want all the numbers greater than 13. So we start at 13. We draw a line that points to all the numbers greater than 13. So I'm going to leave the circle unshaded here because I'm not including 13 as one of the solution. X has to be greater than 13. It can't equal 13. So that's how we solve linear inequalities. Now let's look at graphing regions created by inequalities. So we have to be able to graph things like y is greater than 2 minus 3x. So we have our Cartesian plane. What we're going to do is we're going to start by graphing y equals 2 minus 3x. So when you're graphing the line, if it's greater than or less than, you draw a dotted line. And if it's greater than or equal to or less than or equal to, you draw a solid line. So this is y is greater than 2 minus 3x. We're going to use a dotted line because it turns out this line won't actually be included in our region. So let's graph the line y equals 2 minus 3x. So hopefully you remember how to do this. This is gradient intercept method. The y-intercept is 2, so we're going to plot that, 2. The gradient's minus 3, so that means we always go across 1 to the right. It means we're going to go 3 down, and we're going to end up here in this point. Once you have 2 points that lie on the line, you just join them up. So here we are, the dotted line through those 2 points, dotted line because it was greater than. So what we have to do is we have to find the required region. The required region is the set of all points on the Cartesian plane that satisfy this inequality. So once we've drawn the line, all we need to do is pick a test point that's not on the line. So 0, 0 is usually a really easy test point to pick. You can pick 0, 0 as long as it's not on the line you've just drawn. So here I'm going to pick 0, 0, and what I'm going to do is I'm going to substitute into the inequality and see if I get a true statement. So, substituting into the inequality, I get y is greater than 2 minus 3 times 0. So this is saying 0 is greater than 2. Clearly, that's an untrue statement. 0, 0 does not satisfy the inequality. That means 0, 0 is not part of the required region. What that means is every point on the same side as 0, 0, every point on this side will not satisfy the inequality. So all the points that satisfy the inequality will be on this side. So I'm going to shade this side of the line. So any point in this region will satisfy the inequality, and you can pick them. You can pick the point 2, 2, and you'll see that it satisfies the inequality because I get 2 is greater than minus 4, which is a true statement. So then I'm done. Very last thing we need to go through is the opposite when I give you a graph like this here, and you have to find the inequality. So let's try and find the inequality that's represented in this graph here. So labeling my Cartesian plane, what we need to do is first find the equation of the line that's drawn. So you know that the equation of any line can be written as y equals mx plus b, where m is the gradient and b is the y-intercept. Well, here the y-intercept is clearly minus 2. So I'm just going to rub out b and replace it with minus 2. So now we find the gradient. So remember, gradient is rise over run. So to go from this point to this point, I've gone across 1 and up 3. So the rise, how far I've gone up is 3. The run, which is how far I go to the right, you always go to the right. Start at the leftmost point and go to the right. The run here was 1. I went across 1 to the right and 3 up. The gradient is 3. Therefore. So that means the equation of the line that's graphed is y equals 3x minus 2. So what I need to now find is what I need to replace with the equal sign. Is this region y is greater than 3x minus 2? Is it y is less than or equal to 3x minus 2? That's what we don't know, and that's what we need the region for. So because the line is a solid line, it is not dotted, I know that I'm going to have either greater than or equal to or less than or equal to. I need to find which of these symbols I'm going to replace the equal sign with. So to help me decide which of these symbols I need to pick, I'm going to pick a point that is in the region. So I'm just going to pick this point here, which is the point 2, 0. X is 2, y equals 0. So taking my equation y equals 3x minus 2, I'm going to substitute y for 0, and I'm going to substitute x for 2. So I have 0 and 3x minus 2. 3 times 2 minus 2 is 4. So which symbol should I put between these two? Well, clearly 0 is less than 4. So I should put less than signs. But because the line was a solid line, it would be less than or equal to. That's the symbol that needs to go through. Needs to go between y and 3x minus 2. So I'm going to rub out here my equal sign and replace it with a less than or equal to. So this is the region y is less than or equal to 3x minus 2. That means any point in this shaded region should satisfy this inequality. And we can easily pick any point we want. You know, if we pick 2 minus 2, minus 2 is less than 3 times 2 minus 2. So we know that we're right because any point that I pick in this region here satisfies the inequality. All right, that's really all there is to it. Now, thank you so much for tuning into this video. Sorry it was a long one, but best of luck in your test. You're a superstar. I know you're going to do well. This has been the luckiest maths teacher in the world. Have a great day.